Working great. Hi, so my name's Sam, and I'm from SEML. So I'll just quickly introduce myself. So I am currently a developer advocate for SEML. We just got acquired by GitHub and announced that last week. So I'm technically now a developer advocate for GitHub, but we'll see how that goes. I'm pretty excited for what's to come. And before I was a developer advocate, I was actually working full-time on our main online platform, LGTM. I'm passionate about everything to do with open source, security, privacy. I used to contribute to Signal, for example. Cryptography I love. I'm super passionate about code quality, and I also dabble in stage lighting. This is my Twitter handle and GitHub handle, and all of my slides have my Twitter handle in case you want to take any pictures of that. Any of the slides. So today I'm going to begin with a story. It's a story of many bugs. And it begins with a report on the 7th of September, 2017. My colleague Mo submitted a vulnerability and an exploit example to Pivotal for the Spring framework. Now, this particular vulnerability took advantage of something called the Spring expression language, which is a way that you could describe ways to access certain Java objects from strings. And if you were able to actually execute any of these particular expressions, you could get remote code execution. Now, what this particular vulnerability was it was interpreting certain user data from HTTP requests and concatenating them in some strings that were eventually run as these expressions, which meant that you could have remote code execution on any of these servers simply by sending an HTTP request. So that's pretty severe. So in response, on the 21st of September, Pivotal released a patch along with a public announcement encouraging everyone to upgrade to the latest version, which fixed the vulnerability. Except that it didn't fix the vulnerability. Over the course of the next day or two, Mo had a look at the patch, and he discovered that it was a partial fix. It didn't actually fully address the issue. So the next day, he created a new exploit that took advantage of a slightly different code path, and then sent that to Pivotal. A couple of days later, rather than going straight away and making it public, they did a patch, they sent it to Mo, and then asked him to this time to verify before they told everyone about it. Turned out the patch was incomplete still. So they kind of realized that this technique wasn't really working anymore, and there was something else that they needed to do. It wasn't really good just addressing these problems as they were being made aware of it. So over the course of the next month, they actually decided to do a big refactoring of this particular part of the codebase. And then on the 25th of October, released a new version that had completely refactored away and removed the possibility of this type of exploit altogether. So I'm going to talk about a bit of a different story now. It's also a story of many bugs. This one, for the purposes of the story, will begin on the 27th of April, when a CVE was publicly disclosed that was a remote code execution in Apache Struts 2. Now, Apache Struts had something pretty similar to the Spring framework. They had a language called OGNL, which allows you to access arbitrary Java objects from strings that get executed. And that, of course, allows for remote code execution. Now, these strings aren't supposed to be really made accessible or available to use outside of the internals of the framework, but nevertheless, there was this vulnerability. And pretty similar to the struts one, it was interpreting user data as, I was using user data directly to create these strings that it would then execute. So again, you could just send an HTTP request to an Apache Struts 2 server and get remote code execution. So they fixed the bug, sent out a patch, made an announcement. On the 12th of May, 2016, there was another remote code execution bug that allowed user data to flow to an OGNL string. So same thing again. 20th of June, there was a vulnerability that interpreted user data as an OGNL string. 19th of March, 2017, there was another vulnerability that interpreted user data as an OGNL string. And on the 22nd of September, 2017, and then the latest one, I believe, is this one that was also discovered by my coworker, Mo. Now, there's only so much space on a slide, and I wasn't really able to fit in all the vulnerabilities, so here are the other 10. and they're all the same type of mistake. User data is flowing from an HTTP request and being used to construct a string that they execute, allowing remote code execution. So we have a bit of a problem here. And it might seem like I'm just making fun of these two open source projects in particular. But these kinds of stories are common across the entire software industry. Whether or not it's open source software or not, it could be closed source. It affects all of us. And it's not just the small companies either. For example, Apple published the source code for part of macOS and OS X called the XNU kernel. And this source code is available to download for you to have a look at. And one of my other coworkers, Kevin Backhouse, discovered a remote code execution in a component called the packet mangler. Now, he reported this vulnerability to Apple with a POC. They fixed the vulnerability, pushed out an update. When they later then published the source code for that particular version, Kevin had a look at that source code and discovered that there was still a bug in the exact same block of code that they just put the patch in. So he created a new exploit, sent the exploit to Apple, and then they later had to fix that in another patch or another release. So we're seeing the same kinds of mistakes being made over and over again, leading to vulnerabilities that manifest over and over again. So how do we deal with this? How do we solve this problem? Could we potentially use the information of a new vulnerability as an opportunity rather than just trying to respond to it as quickly as possible? For example, could you, once you've found the root cause of a vulnerability, ask yourself the question, is it possible that I've made a similar mistake anywhere else in my code base? There could be something architecturally about your project that means that you're susceptible to a certain class of vulnerability, or it's more likely to happen. For example, your use of C may increase chances of having certain memory corruption vulnerabilities. Or using something like Apache's OGNL or Spring Expression language might make you vulnerable to remote code execution when you're dealing with user data. So you should try and find similar mistakes elsewhere because the chances are you will find something. Companies such as Google and Microsoft, who have been doing this for a while now, actually have a name for this process, and they call it variant analysis. And for them, it's simply not an option not to do it. So this quote is from a blog post from Stephen Hunter, who works for Microsoft. And he says, after doing root cause analysis, our next step is variant analysis. Finding and investigating any variants of the vulnerability. It's important that we find all such variants and patch them simultaneously. Otherwise, we bear the risk of these being exploited in the wild. And I would highly recommend taking a look at this blog post. It's very good, very insightful. So yeah, so for these companies, it's simply not an option not to do variant analysis. It's a stage of their vulnerability response that happens before making any details of a vulnerability public, so that they can patch the original vulnerability as well as all the variants at the same time. Because if they don't do that, when they do release a patch, other people will take it upon themselves to try and find similar vulnerabilities, potentially reverse engineering the patch if necessary. And then, of course, exploiting it if they can. So how do you do this mystical variant analysis? Well, to be honest, until recently, most of the big players have been predominantly relying on a lot of manual work by their security response teams. So focusing on particularly sensitive areas of a code base that are more likely to have vulnerabilities, or manually checking how data flows through an application using techniques like control flow or data flow analysis, checking the range of values that certain variables can take, ensuring that you're checking bounds correctly, that sort of thing. And often doing this sort of research makes a lot of use of text search tools like grep and AWK, that sort of thing. Using something like an IDE or something else more language aware, like SourceGraph, can be really helpful. It allows you to jump to definition. You can jump through the call graph, make sure that you explore every path. Makes it a lot easier than just using grep. But you can imagine this sort of manual analysis might be difficult. You might follow the call graph, go down a few functions, then find yourself in a dead end, have to go back up and then explore a different path. So this sort of process can be pretty repetitive and time-consuming. It requires a lot of iterative exploration. Manually following call graphs can be pretty tedious. It's also unsurprisingly prone to a lot of human error. So the more complex that a certain mistake that you're trying to look for, or the larger the code base, or the closer the deadline, the more likely it is that something will be completely missed. And it's also simply not scalable. As the size of a code base increases, manually checking for a particular class of vulnerability every time a new type of vulnerability is discovered just becomes infeasible, at least to do it thoroughly. And as, of course, your list of types of mistakes continues to grow, as you're exposed to more and more types of vulnerabilities, if you actually want to check these at code review time, it gives you more and more things that you need to check, and it can either completely slow down code review or just make it ineffective. On top of that, even in the most high-tech companies, the number of full-time developers far, far outweighs the number of people working on security full-time. So, how can we expect these small teams to keep up with all of the code being written by their developers? Okay, so that sounds potentially pretty bleak. You need to do variant analysis, and yet doing so is pretty much impossible to do thoroughly. So can we do better than this? What if we could automate it? That sounds like it could be a good idea, right? We could potentially describe mistakes in a way that allows computers to automatically check for them for us, so that we can find instances of that same mistake everywhere across the code base, using not just syntactic information, but also a bunch of semantic information like the call graph, control flow, data flow, that sort of thing. We could then run it across the entire code base, get a load of results automatically, run it across multiple code bases, and even run it in the future to guard against people making that mistake again. So you could use continuous analysis or periodic checks. Well, you might not be surprised by this, but it turns out that there are a few tools out there that allow you to do exactly that. So Clang Tidy, for example, which is part of the Clang compiler, can be extended to write rules for C++ that take into account both syntactic and semantic information. And Mozilla actually have a custom set of rules that they run against every patch that's submitted to Firefox and Fabricator to catch the sort of mistakes that they've experienced in the past. And this is used pretty extensively by their security teams. And linters as well are starting to include more and more semantic information for their rule sets to use, particularly those that work with statically typed languages. And there's also projects like, I'm not sure if I'm pronouncing this right, Cotinel, which is something that allows you to actually write semantic patches and automatically apply the updates. And here's the main thing that I'm talking about today. There are also a number of technologies emerging that allow you to interactively write queries over the source code that include semantic information, including one solution by my company. But I'm not going to compare all the different solutions in this, or the different technologies in this presentation, but I do want you to know that they exist. And I do as well want to give you an idea of the sort of things you can write, or the sort of checks you can write and look for with these sorts of technologies. So I'm going to go over an example from that same blog post I took the quote from earlier. Just one sec. So this example code here is from Chakra Core. Now, this is the JavaScript engine that powers Microsoft Edge and a bunch of other Windows applications that are written in JavaScript. And this C++ code is part of a built-in function that can be called from within JavaScript. And I'll just go over what it does. So the first thing it does is it gets the pointer to and size of a particular block of memory that represents a JavaScript array buffer. One that's being passed in via the arguments here. And it assigns those values to the local variables pbuffer and buffer size. After that, this call to var to int may potentially run arbitrary JavaScript code because it uses the passed in object's value of method to calculate the value. And I'll explain that a little bit more in a bit. But with this, you could potentially override this value of method to free the buffer. And then when this code returns, pbuffer would be a dangling pointer. So at this point, we don't know what buffer size or pbuffer actually is at all. And when you then later try to use it to perform an operation, for example, looping over the array, you have undefined behavior, because you could encounter a memory corruption or something worse, maybe like a remote code execution vulnerability. And the JavaScript exploit looked a little bit something like this. And in particular, they've overwritten this value of method to then free the buffer effectively. And this is all illustrative code. This isn't actually a live POC, but it's taken from the blog post. So Microsoft assessed this vulnerability as critical, and they wanted to know whether they had any similar mistakes to this anywhere else in the Chakra code. So, as you could expect, they wrote a query or a check that describes the pattern of assigning a pointer of an array buffer to a variable, then calling JavaScript code, and then trying to use those variables. And this is more or less what the query looked like. I've modified it a little bit here to fit into one slide, and I'll go through it and explain it. But for anyone that's used a database query language like SQL, you'll see pretty familiar concepts here. We have a from clause that lists all the relations that we're interested in looking at. So in this case, we're looking at variables, assignments of array buffer pointers, function calls, and accesses to variables, which is either something that's a read or a write. We then have a where clause that lists some conditions that need to be satisfied. And we have a select that lists all the columns that we want to output. Jumping into the where condition, this line ensures that the pointer assignment and the variable use are talking about the same variable. So in our example code here, it's checking that they're both talking about the same variable pbuffer. This line ensures that the function call is to a function that may potentially execute JavaScript code. Now, rather than enumerating every single such function in the Chakra code, you can imagine there's quite a few, the security researchers knew that any code that calls back into JavaScript eventually calls this method, or calls the function method call to primitive. So rather than saying, so they could simply say, they could use a call graph to say, anything that may eventually or transitively call this function is something that we care about. So they might call method call to primitive directly, or they might call a function that calls method call to primitive, or they might call a function that calls a function that calls method call to primitive, etc. So that's what's expressed here. And if you want me to explain that in more detail, you can, of course, ask me after the presentation. So that's this function here, ensuring that this might potentially execute JavaScript. And then the last two clauses, this one says that the call to JavaScript happens after you assign the value to the variable. So that happens first, and then the call. And this next one says that the use of the pointer, the use of the variable happens after the call to JavaScript code. So it ensures that. Now, in this Microsoft blog post, Stephen Hunter said that this query, in addition to matching the original vulnerability that they were using as a seed, it found 4 additional variants that they also assessed as having critical severity. So they were able to not find just one vulnerability, but find 5 at the same time. So that example was very specific to the Chakra code base, but there are many kinds of mistakes that are a lot more general. For example, something that's a misuse of a particular language feature, or mistakes that are commonly made with certain APIs or frameworks. And in those cases, you can actually go a step further, and rather than just running on your own code, you can make your checks open source and freely available, share them with the world, so that anyone else that has code in that same language or uses that same framework can benefit from your check and ensure they don't make the same sort of mistake. And beyond that, you can also take advantage of the queries and checks that other security teams are open sourcing, especially if you're running anything continuously, and just keep adding these queries to your check so that you will find everything you need to. So let's have a slightly different story now to sort of illustrate this. Who here has heard of ZipSlip? Okay, cool. I get to explain it. So like all cool vulnerabilities, this one had a logo. So this was originally discovered by SNCC, and they did a blog post about it. And I'm going to explain exactly why it's important in a sec. So to understand this vulnerability, the first thing you need to do is understand exactly how zip files are structured. So you may think that because they usually contain directories of files, that there might be some sort of tree-like structure. However, zip files are simply lists of entries that include the metadata, the name or path of the file, and the data themselves. And notably here, the path is just a string that might contain slashes in it, which will indicate when something's in a certain directory. Now, you might think, could I put arbitrary strings in the file paths here? And you would be right. And SNCC realized this and thought, I wonder if anyone is just joining these strings onto the end of target directories when they're writing unzipping code. And it turns out that yes, this was happening everywhere. In every single programming language, there are dozens of projects that are writing unzipping code that just joins the path onto the end of a target directory. So you could potentially create strings like this. And if you're running a particular application as root, you might be able to simply by trying to unzip a file, you might be able to override the cron tab and get remote code execution. Or even if you're not running as root, you could still probably get remote code execution by overwriting the bash profile, stuff like that. So here's some example Java code of insecure unzipping, which is understandably, this sort of code is everywhere whenever you look over Stack Overflow. This is the correct way to unzip files in Java, except this line is particularly problematic because it is disjoining the path of the zip entry to the destination. And the fix for most programming languages, if you're writing unzipping code, is only usually a couple of lines. Here it simply checks that when you normalize the path and collapse all of the path traversal elements, that it's still within the target directory and hasn't actually, isn't trying to unzip it to anywhere outside of that. So when SNCC published this vulnerability, Microsoft caught wind of it, and they wanted to know if they were making any sort of mistake similar to this elsewhere or anywhere in their code. So they wrote a query to search for this pattern. And this particular query was for their C# code. And it looks for data flowing from a zip entry path to any IO operation without some sort of sanitization along the way. So they ran it across their code, found a number of results, fixed it. But then the next thing they did was they open sourced it so that other people can take advantage of that. Now, raise your hand if you write any C# code. Cool, there's 4 people in the audience that do. Well, so there's a C# query that you can use, it's freely available for you to use, that will check for this sort of vulnerability. My company also went ahead and wrote similar queries for different programming languages, so you can probably find automated checks online for your stack to find this sort of vulnerability. So you might, at this point, potentially be interested in if you can use variant analysis yourself, if it makes sense for your company. If not, then I need to improve this talk. But I'm going to assume that you do for now. And I'm also for now going to assume that you already have some sort of workflow in place for dealing with vulnerabilities that you find in your own software. If you don't, we'll briefly talk about that in the next slide. So let's assume you have a workflow in place. It probably looks something like this. You receive information about a security bug. It might be through a bug bounty or pen testing or code review, something like that. You diagnose the root cause, investigate what's wrong, fix the problem, and publish a patch to your users. Well, the most obvious place for something like variant analysis to fit in would be as additional steps after you diagnose the root cause. So firstly, what you would do is you would describe the mistake as a check or a query in whatever tooling that you're using, be it Clang Tidy or anything else. You would then run this query against your code base to see what results you get. Now, to begin with, you'll probably end up with a whole bunch of false positives because there'll be things you didn't account for, reasons that mean that the code isn't actually vulnerable. So you have a bit of an iterative process. You improve the query, you reduce the false positives until the results are small enough that you can kind of triage it manually and go through and make sure that, or check whether each particular bit is vulnerable. At that point, you can fix all of these variants at the same time. And at that point, you actually then deploy the fix to your users so that there isn't an opportunity for other people to find those variants before you. Beyond that, now that the query is actually written, you could potentially run it on a regular basis, monitoring it continuously, potentially as a nightly thing, or maybe you could even integrate it into your code review system for your developers. And for example, if you find it in code review, you can then discover these variants before the code has even been merged and fix it right then and there. And this is effectively what Mozilla are doing with Clang Tidy with their custom rule set that they've written. So beyond this, like I mentioned a minute ago, the final ideal step would be to share this query that you've written, if it's general purpose enough and it makes sense, with everyone else, open source and allow other people to take advantage of it. And then, of course, bring in the external knowledge from security teams from outside your company to also check for things that they've found in their code. And with this whole process in place, your software will probably have far fewer vulnerabilities caused by repeated and easily preventable mistakes. So what about for those of us that don't actually have a security response process? For example, you might be part of a small software startup, or you might be working on a bunch of open source projects. Well, the first thing to understand is that sooner or later, if you're developing software, you may very well be faced with a vulnerability. You probably will be faced with the vulnerability that you need to deal with. And it would be good to have an idea of exactly how you would go about dealing with that situation. But in the meantime, until you get your first vulnerability discovery, I would highly recommend making some sort of automated security checks part of your workflow. Just add all of the tools, use all of them, especially if they're freely available. There's no excuse really not to. Automatically analyze your pull requests for things that are well known and talked about, and take advantage of all this knowledge that's being shared by the expert security teams from all these large tech companies. So I'm getting pretty close to the end of my presentation. I'm kind of whizzing through it. But before I close up, I wanted to talk about a couple of things that variant analysis is not, to alleviate any confusion. So variant analysis is not a replacement to good software architecture. If you're encountering lots of memory vulnerabilities, I would still recommend migrating to Rust if you're considering that. If you're using expression languages like they were in Apache Struts and Spring, maybe don't. And if you have like SQL operations that you're doing, perhaps I would consider using auto-escaping database libraries to completely eliminate that sort of vulnerability entirely. Variant analysis is not a replacement to exploit mitigation. Things like address space layout randomization and stack canaries are very, very important things to reduce the damage that someone can do when a vulnerability is found. Every layer of security is important, and using one is not an excuse to not use another. And finally, variant analysis is not a replacement to other security practices. If, for example, you're doing fuzzing, it actually complements that sort of thing very well. You might find a bug through fuzzing and a certain sort of mistake, and you're like, I wonder if this exists anywhere else. And then instead of finding one vulnerability, you find 5 or 10. It's also, not a replacement for doing vulnerability disclosure or bug bounty programs or audits or pen testing or red team exercises, etc. All of these things I would highly recommend that everyone does if they're creating software, because the more security checks and systems you have in place, the better. So at this point, you might be interested, okay, you've told me variant analysis is pretty good, and I want to know how I can actually start using it myself. So I'll give you a couple of pointers. I'm not going to recommend that you use GitHub software specifically for this. That is a choice for you to make, but I do want you to consider what variant analysis could do for you, and if this story that I've told today is something that makes sense to you and you feel like it actually affects you. So hopefully with these ideas that I've given you, you'll be able to reduce the amount of manual work you're doing and potentially improve the software security of your software. So if you're writing or maintaining software, look at what other tools other teams are using. Look at the large enterprises. Look at smaller teams. See what they're blogging about. See what they like. And then try out a bunch. See what lands and works for you. You might find that certain tools make more sense than others, but they probably will all fit into your workflow in a similar way. And if you're a blue teamer or a security response or a security researcher, experiment writing checks for vulnerabilities you found in the past using different tools. See what feels easy, what actually improves your workflow. Is there anything that allows you to get a bunch more bug bounties because you found many more vulnerabilities? And, there's a whole bunch of blog posts out there by many different security researchers doing variant analysis at the moment. So go hunt those out and see what everyone's saying. So to recap, you should do variant analysis. Better yet, you should do automated variant analysis. You can use and contribute to the shared knowledge and checks that's all open source that exists out there in whichever tools you prefer. Checks should be run continuously, not once off. Mistakes that are made in the past are very likely to be repeated in the future, so you want to protect against those as well. And then finally, variant analysis is a process that complements and doesn't replace other security practices. Don't use it as an excuse not to do other things. You should do everything, ideally. All right, that's all I've got. Thank you. Welcome questions.
Okay, so can you please raise your hand so I can give you the mic? Okay.
Thank you. How is variant analysis different from SAST and writing your own custom rules for SAST?
It's not. It's a process, and SAST would be one of the tools that would allow you to do variant analysis. So it describes more, it's more a name for the process rather than a name for a particular capability of a tool set. So the idea is that you want to embed it as part of your security response process. It's not simply enough. Most people that use SAST, as far as I have seen and experienced, they mostly sort of do it as a set and forget thing. It's not something that you're usually actively contributing to and configuring. Most people sort of like, cool, I've got SAST, my developers are getting reports, they're either fixing them or not, or whatever. It's not that often the case, or it hasn't been that often the case until more and more recently that people are actually configuring SAST to find more and more things, and certainly not for every single vulnerability that they're experiencing, which is the key thing here.
How do I get us started with this type of approach without paying your company?
Good question. So if you want to get started playing around, if you want to use my company's in particular, it's free for open source projects, so you can play around with using it for open source code. If you don't want to pay us, but you want to play around with proprietary code, then you can run a POC. And for other tools, I would just recommend using whatever their process is. So there are other commercial tools that have that you can then go through their trial process, and there are tools like Clang Tidy and Continental, and you can just that are open source, and you can just play around with them for free. So does that answer your question? No. Okay. You can ask me more stuff afterwards. Anything else? No. All right. Thank you.